for 4th of July, let's try to make something fun. So I've actually done this before, but I'm going to redo it, and I'm going to make fireworks in Python. So I'm going to start with this basic program of just projectile motion. I'm not going to start from scratch. So this is, and if you're not familiar with Web VPython, it's Python, but it has a bunch of 3D elements in it. So this is just your plain basic projectile motion. I'm going to go over this, and then we're going to modify it and make it better, and then we're going to modify it again and make it even better, and then maybe even again. And it may not work, but that's the challenges that we have creating stuff that will come across errors, and that makes it fun. Okay, so this program right here is just your very basic numerical calculation. Let me just go over the different parts of this. Is that big enough? Can you see it? That's plenty big, right? I think so. Okay, so 3D objects in Python, two of the objects that we're going to use are the box and the sphere. So the box is the ground, and that's just a box. I give it the dimensions, I give it the location, which is the location of the center. The color, boring. It's not even really there, it doesn't really matter. And then B1 is my firework. Gets shot into the air. I give it an initial position. Why did I give it an initial Z? A negative. Oh, I think I moved the whole thing down so that it would just automatically zoom in. And this is a great feature right here, make trail. So if you do that when the object moves, it leaves behind a trail, and that's cool. This is my gravitational field, initial velocity, initial angle, the mass. I'm just picking stuff here. And then I assign it as a property there. I don't know why I did that. I copied some code I'm going to change, though. And then I give initial velocity for the ball as a vector, right? Cosine theta, sine theta. And then I give a momentum, time step. And then what I'm doing is each time interval, I'm going to calculate the force, which doesn't change because it's just projectile motion. And then use that to update the momentum. That's what this is, update the momentum. Use that to update the position, and then update time, and do it over and over again. And that's your basic projectile motion. Okay, let's do this. Let's run this just for 1 second. Oh, I do have more stuff down here. Let's just delete all that, because I don't know what that is. Okay, so now I just have, while t is less than 1, it's just going to run for 1 second. That's going to be my launched firework. So let's just run that. And then what I want to do, I'm going to start off very simply. I'm going to make it break into two fireworks. Okay, 2 balls. So let's do that. Let's just stop this. Let's delete that object and replace it with 2 more balls. So we can do that. So down here, I'm done with my launch phase. I can say b1.visible equals false. So that means it just disappears. It's still there. It just, you can't see it, which is fine. And then let's make 2 more balls. I'm going to say B2 equals sphere, and the same position for now. Position equals B1.pos. Radius equals, let's see, what was my radius of my other one? It was 0.2. So let's make it half the size, right? So let's say radius is 0.1. I mean, that sure they'd be half the volume, but it doesn't really matter. And let's do this. This is my favorite part. Color equals vector. Random. So you can make, let's see, is that to color? That's right. Okay. You can make a color using the RGB colors. Okay. So I can do something with red, green, and blue. How did this whole thing get moved over? That's fine. Red, green, and blue colors, if you give it a value between 0 and 1. And so random gives you a value between 0 and 1. So this will give it a random color, just for fun. Also, I want to make trail true. So let's see. Let's put this. Oh, you can't see that. Let's just return it over here. Make trail equals true. I need to give it a velocity and momentum, but let's do that in a second. And then I'm going to just say, let's make another one. Then call that one B3, and we're going to change this. Same thing. Everything's the same. Okay, so now what I want to do is to run it for another second and just calculate, update the momentum and stuff for that. It will be boring, but so I'm just going to copy this, paste it, and I'm going to say while t is less than 2, so it's going to run for another second. And I'm going to calculate the force. I'll call this F2, B2. I need to do the same thing for B3. So let's call that 3. Oh, I want not 1, 2, 3. 3. Actually, that's 2. That's 3, which is stupid, but I didn't give them a mass. I should do that. Okay. B1, B2.m equals m, B3.m equals m, I need the momentum. So let's say B2.v equals B1. Let's just say P. B2.p, no, yes, equals B2.m times B1.p divided by B1.m. So B1.p is the momentum at the end. I never updated the velocity. And so this will give it the same velocity, but not the same momentum. It doesn't really matter, but there we are. And then B3.p equals B3.m times B1.p divided by B1.m. So they have the same velocity, which is not what I want. That's fine, though. Now I need to update the momentums. B2, 2, 2, and then I'm going to do another one of those for 3, 3, 3, 3, and then I need to update the positions. 2, 2, 2, 2, and now I need to update the other one. 3, 3, 3, 3. Okay. Let's run it. So there's the first second. And then they turn into 2. There's 2 balls there. That's actually pretty good. And they're different colors. But they're right on top of each other, so that's not that much fun. Now, we want to think, how do you make something explode? How do you make something explode? Well, I could just say the total momentum's the same and split up the momentums in random values. But I want to make it more physicsy. So I want to actually make an explosion. I'm trying to think right now. I want to just exert a force on them. But what I want to do is to kind of make the spheres in some random position. And if they overlap, just push them apart. That'd be realistic, right? I like that. And then so it could be pushing apart in all sorts of different directions. So let's do that for 2 masses, and then we'll do it for 20. We'll break this into 20. So and then we'll add air resistance. Air resistance is easy. That's what we're gonna do, and I'm gonna stick to it. I'm gonna do it. Okay. So I need a spring constant. Let's put that up here. K equals 500. I'm just picking a value. We can change that later if that doesn't work. And so what I want to do here, when I make these 2 new balls, I don't want to, if I put them right there, it's not going to work. So I need, let's call this spacing parameter R, and that's going to be how big of a ball they're going to be in, or how much variation. That's going to be the variation from the center. So my ball has a radius of 0.1. Let's call that RB is 0.1. That's going to be the radius of these things. Let's put it right down there. RB. That's the radius of the ball. RB. And then let's say R is the radius of the new balls. So that's going to be 0.2. I'm just making up something. Okay. Now, when I make their position, I want them to be related to the original thing, but I want to add on a vector. So I want to add on a vector that just puts them in some spherical distribution. So I can make a spherical distribution. Actually, I can make a square distribution, which is what I'm going to do because it's not really going to matter. So let's just make it in a square distribution. So I can say plus this R parameter times vector 2 times random minus 1, 2 times, and you got to spell random right. It's not random, random. 2 times random minus 1, 2 times random. So 2 times random minus 1 gives you a number between -1 and 1. And then then I multiply it by that R parameter, and that tells me the spacing. So this is going to make them kind of distributed. And I can just do the same thing. Let's just copy that for this other mass on here, and let's just run that. Did I copy the plus? No, it didn't. Plus. Okay. So now they're going to have some random position, so they will look a little bit different. Let's just see what that looks like. Oops, I zoomed out. Yeah, there. So they're still projectile motion, right? But they're a little bit off. And it looks like they're not going to overlap. So I want to make that position a little bit smaller. Let's make that R 0.1. Let's just do that. Okay. So now what I want to do is when I calculate the force, I think I can do this. Let's give them both a property of F. B2.F equals vector 0, 0, 0. B3.F equals vector 0, 0, 0. And that's going to be the net force associated with that. Now what I want to do, and I don't need to use this, so let's just change all this. B2.F, B3.F, and then this will be B2.F, B3.F, and that everything should be working. Let's just run it to make sure it works. And boom. Is there two there? I think there's just one dark. Yeah, one's purple. Okay. Now, let's say I want to see if they overlap. If they overlap, I'm going to calculate a spring force. And so I've done this a couple times before. Let's see. How do we do this? So I'm going to say, let's calculate a temporary vector. So I'm going to calculate that gravitational force. That's fine. And then I'm going to say R temp equals B2.POS minus B. This will be from 3. Let's do 3.POS minus B2.POS. So it'll be from 2 to 3. And then I will say if the magnitude of R temp is less than 2 times RB. So if it's less, the distance between the two objects is less than the overlap, then I'm going to calculate a force. So I'm going to say the force is going to be equal to, see, how did I calculate this before? Then it will be the force, so it'll be, I'll say B3.P, I'll get this backwards, B3.F equals B3.F, the old force, because I still have gravity, plus minus K times 2 times RB minus mag R temp. So 2 RB minus mag R temp is the compression amount, right? How much it's compressed. And then that's the spring constant, which I have to put a multiply there. And then I need to make this a vector. So I'm going to say times norm R temp, right? So that makes it back into a vector. And then I need to do the same thing for B2.F. It's just going to be negative B3.F, right? Because the forces come in pairs. And I think that should work. Let's see. I'm going to make this go a little bit faster because I'm impatient. This first one. So let's run this at 3 times speed. So it'll only take 1/3 of a second. Let's see. Let me get my thing back up so I can see. Okay. Run this. Oh, error. Cannot subtract a vector and a scalar. Okay. Cannot subtract. Okay. It must be right here. RB. Where's my vector and my scalar? Mag R temp. Let's just see if it gets here. It did print that. Okay, this is troubleshooting here. This is live coding. We're not messing around here. So it's maybe B3F is a scalar? No? Let's put it right here. Oh, it did that time. Oh, you know why? Because it didn't overlap. So there's a problem here. Let me run it again. Yeah, so there is the problem right in here. B3.F equals B3.F minus K times 2 times RB minus mag. Oh, that's why. This needs to be there, and that needs to be there. Ha. Okay. It was a parentheses error. Let's try it again. Okay, that one didn't overlap, I don't think. Okay, that one did. I like that. Okay, so let's run it one more time. Now, this is a great problem because look at that. That's pretty cool. I'm pretty happy with that. So this isn't one. There's a physics problem where you like shoot a ball into an air and break it into pieces, and you look at the center mass or you look at the motion of the two, and that's what this is. But it's random, and I'm pretty happy with that. Now all I need to do is do like 20 balls. Let's just change this to 20 balls. We're making good progress here. Okay, so instead of this B2, B3 stuff, let's make N balls. So I'm going to go right here, and I'm just going to, I don't like to delete stuff. So I'm just going to comment it out. And this tick mark comment, I think only works in Web VPython. I don't think it works in Python. So let's say N equals 10. I'm going to make 10. N equals 0. This is my favorite way of counting. It's maybe not the best way of counting, but the way I like to do it. And I'm going to say while N is less than N, and then I'm going to say N equals N plus 1, so it'll go through the whole thing. Now, let's make our balls. I'm going to call it a list, an empty list. And I'm going to go through and add balls to my list. So let's just say BS equals BS plus a sphere. And I'm going to copy this thing right here. See, b1.pos plus r times vector random. Yeah, I think that's fine. Okay. Except this needs to be tab. I think that needs to be tabbed. I don't know. Let's just get it over here. Make trail. That's fine. So now that's going to make a list of balls. And let's just comment out the rest of the stuff, and let's just see if it actually makes all the balls. Because I still need to set the forces and stuff. Okay, let's see. I think it did. Yeah, there's a bunch of balls right there. Awesome. Okay. So the next thing I want to do is I need to give them mass, momentum, and everything. So let's say this. I could do it all in the same loop, but I'm not going to. For B in BS, B dot M equals N M divided by N. Each one has an nth of the mass. It doesn't really matter, but I'm going to do that anyway. B dot P equals B dot M times B1 dot P divided by B1 dot M. So again, I'm setting the momentum of each piece based on the velocity of the original piece. So they're gonna have that momentum. What else did I set? The force. B dot F equals vector 0, 0, 0. Okay. So now down here, I'm going to skip over that part, but I do want to get this back in. Go back over here. And now I don't have this force thing, right? So I'm going to need to set the gravitational force. So let's do this. And I'm going to go through a double loop. I'm going to go through let's go through and set the gravitational force, which may not be the best thing. So for B in BS, B dot F equal, I don't have to do that once. Now I'm going to reset it. I'm resetting all the forces because I'm going to see if they're overlapping. And if they're overlapping, I'm going to push them apart. If they're not overlapping, then they have the gravitational force. So it's going to be B dot M times G. Don't need that. Now let's do this. For B in BS, and then I'm going to say, oh, actually, I should do this. I should do it right in here. So once I reset the force, now I'm going to check the force with all the other masses. So I will say for A in BS. So I have two balls, A and B, out of the list. And I want to see if they overlap. So let's first calculate the vector from A to B. RAB equals B dot POS minus A dot POS. Right? That's that vector. And those are just two random positions. They could be the same thing, right? So I have to make sure, what do I have to make sure? If they're the same one. If I have this. If mag RAB is less than 2 times RB. right? So if they're overlapping. And I'm just thinking, right? Because if A and B are the same thing, then they overlap by definition. How to prevent that from happening? How did I do that before? Well, I should say something like, if it's less and greater than zero. If the overlap, if mag RB is 0, then I have a problem. Right? Yeah, let's do this. If mag RB and mag RB RAB is greater than 0. Yeah. I don't know if that's going to work or not. Then I can calculate the force on A dot F equals A dot F minus, because I need to add it to the gravitational force, minus K times 2 times RB minus mag RAB. And then all of that times norm RAB. That's what I had before. Yep. Okay. So that's going to calculate the force. This double loop's going to go through and calculate the force on all the things. Now I need to go, and I don't need this. I'm not doing this. I'm not doing any of this. Now I need to go through and update the momentum position. So let's do another loop for C and BS. C dot P equals C dot P plus C dot F times, no, that's an A, C dot F times DT, C dot POS equals C dot POS plus C dot P times DT divided by C dot M. And that should do it. Let's see. Save. Run this thing. Run it. Okay. That worked. I mean, it's crazy, but it worked. And it's actually kind of awesome. So I do want to, I can do a couple things. I can reduce that spring constant. So let's make this 100. And let's see what happens. Okay. That's legit. That's legit. Okay, let's make it 75. 70. Okay. Now that one keeps going up. Is it going to come down? I think it is coming down. Now, if you want to, I'm going to give you the code. A great homework would be to see if momentum is conserved. If momentum is conserved, that's a pretty good check that things are going in the right way and you're making good fireworks. Energy is not going to be conserved. Kinetic energy is not going to be conserved because we're adding energy to the system with this overlap stuff. Okay, I'm going to do one more thing. I'm going to add drag. And I'm going to add linear drag. It doesn't really matter, but I'm going to add linear drag. So let's say the drag coefficient C is 1. And I'm going to say just the CV is my drag. So I can do that down here. So right here, when I calculate the total force on each one, I'm just going to say minus C times B dot P divided by B dot M. And that way I don't have to take any magnitudes or anything like that. And that's going to give it a drag force. Right? Yep. Okay, let's see what happens. Oh, too much drag. Look, they just stopped. They're still falling though. Look at that. They're still falling. Okay, I like that. So, simple fix. Decrease the drag. So I'm going to make C 0.1. Okay, that's pretty good. Let's make it a little less drag, 0.04. That's pretty good. Okay, now for fun, what if I have, I don't know, 100 masses? Because that's just 10, right? So I can change that. So all I'll do is go up here. Where do I do that? N equals 100. I should go 50. I'm gonna go from 10 to 100. That's just bold. Oh, okay. So if I increase to 100, they're all overlapping, right? My overlap distance is too high. So I really should have this where I check for this distribution. R needs to be bigger, or RB needs to be smaller. But then if RB is smaller, oh no, I can make RB smaller and then just keep the size of the things the same. Let's do that. So let's just change this radius is just R. Okay. And then I'm going to make this RB, which is the overlap distance, smaller. So it's going to be RB divided by N, which I can't do because I didn't declare N yet. So I'm going to cut it and put it down here after the N. So now the overlap distance should change, right? Because it's going to be smaller the more pieces I have, so they won't overlap as much. Or at all. Okay, so let's say, what if I do the square root of N? I want it to overlap a little bit more. No. Well, I need to increase the spring constant then. Oh, you know what? The drag force. It seems like they're just stopping. Why are they stopping? Let's just say, let's just put this at 0.01 and see what happens. See why? What the heck did I do wrong? I like to bear the other way. What can I do? What did I do wrong? Let's put that 0.1. Does that work? Okay, that did work. Okay, let's make it a little bit smaller. 0.5. Okay, there. Okay, so I think you could fix that better, but that's pretty good. That's your 4th of July art right there. Now, momentum will not be conserved. Okay, I said check if momentum is conserved. It will not be conserved because there's that drag force on there. So the momentum, unless you turn off the drag force and see if momentum is conserved, add the drag force and then you can do that. So there's your code. I'm pretty much done with this. Happy 4th of July. I'm going to save this, saving it. I'll give you a link to the code. Python fireworks are safer than real fireworks.